Right, so today I'll be talking about Tracy-Widom bike-range distributions in the spatio-temporally chaotic state of the one-dimensional Kuramoto-Sivashinsky equation. Okay, and I will explain every word in that title to you as we go along. This work has been done not by me, but by Dipankar Roy, whose photograph you see here. He's in the audience, so he will answer all the hard questions. We have support from these funding agencies who have very kindly supported us for several years. Okay, so here's an introduction. Most of you must know about the Kardar-Parisi-Zhang equation, which has many nice properties. For those of you who don't, I have a brief introduction. And then I will tell you about an equation which some of you might not know about, the one-dimensional Kuramoto-Sivashinsky equation, which in some sense that I will make precise is supposed to be in the KPZ universality class. And then there are some new types of distributions that people have been looking at in the KPZ equation, which, as far as we know, have not been studied in the Kuramoto-Sivashinsky context. So that is what this talk is about. All right, so the KPZ equation, I think all of you probably know. It is an equation for h of x comma t, which is the interfacial or height profile. Nu, lambda, and d are parameters, and eta is a zero mean Gaussian white noise. So this is a celebrated stochastic partial differential equation studied first by Kardar, Parisi, and Zhang in 1986 to model a growing surface or a growing interface. Now, it turns out there are many related models, and their relation with the KPZ has been elucidated in many studies. One is the so-called polynuclear growth model, weakly asymmetric exclusion processes. You heard about these in Arvind Iyer's talk, at least some exclusion processes. There's also the stochastically forced Burger's equation, which follows by the substitution u equal to minus lambda partial derivative of h with respect to x. And then a Hopf-Gold transformation takes you to directed polymers in a random medium. Okay, so there are many models which are in this class. There's a lot of things known about the statistical properties of the KPZ equation. First look at equation 2. I'm not pointing on this slide because of the, grazing incident. So let's look at the height as a function of time, subtract from it its initial value. Then it has been found by several numerical and other experiments that this is growing linearly with time first, with some coefficient which we will call h infinity. And then there is a dependence on time with an exponent beta kpz and some variable here, which for the moment I'm calling chi x comma t. Okay, and this is for large time. All right, the first set of studies looked at exponents like beta kpz, which was found to be 1/3, and these can be found exactly for a variety of reasons that I won't go into, and also a dynamical exponent z, which is 1 over twice this exponent, which is 3/2. In particular, z is what comes into the temporal evolution of the width w sub L of t for an interface at time t in a system of length L. This was in the first round of KPZ studies, and in those days, people who studied the Kuramoto-Sivashinsky equation, which I'll tell you about in one more slide, they checked that the Kuramoto-Sivashinsky equation also gives these same exponents, beta kpz and z kpz, but it takes a lot of sophisticated numerical work. I'll get to that later. In the second round of studies, the so-called second revolution of KPZ, people looked at this variable chi of x comma t, and it was found that it has different limiting statistics, that is different PDFs or probability distribution functions for different initial conditions. For the so-called flat, and I'll give you examples of these, you get the celebrated Tracy-Widom PDF, which you heard about in Anjan Kundu's talk this morning, which gives you Tracy-Widom Gaussian orthogonal ensemble. Or in the statistically stationary state, you get another distribution called Bike-Rains. And then in the curved or wedge-shaped initial condition, you get the Tracy-Widom, but this time for the Gaussian unitary ensemble. And these PDFs should appear for all models in the one-dimensional KPZ universality class. These Tracy-Widom type distributions were perhaps first discussed in the random matrix context for the largest eigenvalue lambda sub m, as was discussed in Anjan Kundu's talk. And then the Bike-Rains one was studied in a related model called this polynuclear growth model. All right, so let's get to the one-dimensional Kuramoto-Sierraszynski equation. Unlike the KPZ equation, this is a deterministic partial differential equation. So it's an extended dynamical system, and it's of the same sort roughly, no noise, but you have diffusion with the wrong sign. So left to that itself, it would just explode. To control that, you can put in a higher order derivative. For those of you who do fluid dynamics, that would be, these two would combine to give a hypoviscosity. And then there is the same KPZ nonlinearity. If it were not for the nonlinearity, this equation would be unstable. The nonlinear term seems to combine the unstable modes, and the system reaches a statistically steady or a state with spatiotemporal chaos, which is reminiscent of turbulence. In fact, people use this as a simple model for turbulence. All right? It was shown by a variety of people, all the references are given here, that if you look at sufficiently large times and sufficiently large lengths, then the statistics of the height in this Kuramoto-Sierraszynski equation in its spatiotemporally chaotic or turbulent state have the same exponents beta KPZ and Z KPZ as the ones I just described for the KPZ equation. But to the best of our knowledge, nobody has looked at this extra object called chi, which I will just remind you, this chi over here in equation 2, which, if we believe in all this universality at a detailed level, should follow this Tracy-Widom Gaussian orthogonal, Tracy-Widom Gaussian unitary, and the so-called Bike-Rains PDFs, if we look at the correct sets of initial conditions. So to do that, you have to have the numerical expertise, which Dipankar certainly does. It's a pseudospectral code, sufficiently well done, so let me not bore you with that. Here are the three initial conditions. The red one is IC1, which is basically flat, except for a little perturbation at x equal to 0 to start it going. Here is a zero mean initial condition, the green one, which is mean 0, but it fluctuates about that. And here is the so-called wedge or curved initial condition shown in blue. If you run these out in time, this is how the spatiotemporal evolution looks. Okay, IC1, IC2, you see the interface getting all sorts of ripples on it, and it now makes for a nice movie, but merely by looking at these movies with your eyes, you will not be able to tell whether they have different statistics or not. For that, you have to do certain calculations. The objects you calculate are given here. In blue is the root mean square fluctuations of the height infinity, which is what goes into the linear term that I talked about. You can worry about the skewness. Most important, you should look at the rescaled height fluctuations, which are hxt minus hx0 minus sh infinity of t, divided by t raised to the beta kpz, the beta kpz being that power. Okay, so can we do this? Well, certainly Dipankar can. Here is a plot for the first type of initial condition of the width versus time for two different lengths. The blue one is L 2 to the 16. The black one is L is 2 to the 20. As far as I know, these are the largest simulations ever done for Kuromoto-Sivashinsky. And the black one, 2 to 20, is doing pretty well according to this power law. You can find the energy spectrum if I use turbulence language. It is HK, H minus K. That has the required power. Please don't look at all the details. The arrows indicate the fitting intervals. You can find the skewness, etc. And to make a long story short, you can do it for the second initial condition. You can do it for the third initial condition. And at the end of the day, you can find the PDF of this chi. And for the right initial conditions, again, don't look at the details, we can get the TWE, Tracy-Widom, GUE. We can get the Tracy-Widom, GOE, and we can get bicranes for the right sorts of initial conditions. Okay? So things are working out as they do, as they should, but it requires a lot of great numerical analysis, which Dipankar has done very, very carefully, and we are still, sort of dotting all the I's, crossing the T's, but I won't bore you with the details. You also heard about a third order phase transition in Anjan Kundu's talk that will also exist here, and so let me not tell you any more details. So what have we done? We have demonstrated how to get these three distributions in the 1D Kuromoto-Sivashinsky equation. If we play with the initial conditions, we can get crossovers from these types of distributions from one to the other. As far as I know, this is the first time these PDFs have been found in a deterministic extended dynamical system that displays spatiotemporal chaos. And we also conjecture that it will work with any nonlinearity. You could have a polynomial function of gradient h as long as it's even powers of gradient h, which is based on a result of Quastel and Hira for the 1D KPZ equation. I thank you.
Questions?
Okay, fine. Sorry, there's a question. Yes.
Okay, so for the KPZ equation itself, I mean, so this has been also seen accurately in numerics?
Yes.
I mean,
I can flash one thing for you, but the short answer is yes, by Halpin Healy and Takeuchi.
And that, but that's not chaotic, is it? I mean,
no, but that has the noise.
With noise.
With noise.
Right, yeah.
KPZ is noise.
Yeah, of course.
Right, sure.
So if no more questions, let's thank the speaker.